Welcome to another podcast. In this episode, we're going to be taking a look at Simpson's rule, and I have an integral in mind. We're going to look at the integral from 1 to 4 of the square root of x dx, and I'm going to calculate the S6, and then I want to ask how much error is committed. So what is the total error expected versus observed? So let's start with the S6 calculation. First thing we want to do is calculate our delta x. Delta x is b minus a over n, which is 4 minus 1 over 6, or 3/6, or 1/2. Because of that, this should be a pretty nice timeline. We're going to start at 1 and count by halves. So we've got 3 halves, 2, 5 halves, 3, 7 halves, and 4. And so there are the important points for doing Simpson's rule. If I count everything out, we've got S6 is equal to delta x, which is 1/2 divided by 3, so this is 1/6. And then the function here is square root of x, so it should be 1 times the square root of 1, 4 square root of 3 halves, 2 square roots 2, 4 square root 5 halves, 2 root 3, 4 root 7 halves, and then finally the last point is just the root of 4. So remember the order this goes in. The outer points are weighted 1 each, and then it's 4, 2, 4, 2, 4. So that's the weighting scheme that we're using for this particular answer. And if you calculate everything inside the parentheses there, you'll get 33.99937, which, actually, sorry, that's incorrect. If you calculate everything in the problem, you're going to get 4.666563 as the approximation. So this is what S6 is equal to, and so the integral is approximately equal to that value. Now, we can actually find the integral itself. The integral itself is the integral from 1 to 4 of the square root of x dx, which we should recognize as being a power rule. And so when I take the antiderivative, it's 2/3 x to the 3 halves. And when I evaluate this from 1 to 4, this is 4.6 repeating. And so you can see right away that we have a very good approximation. We're accurate through at least the 3rd decimal place. And the question that we want to ask now is the error between these two, is that something that was predicted by our model? So the error between these two is I minus S6 in absolute value, which is 4.666563, minus this one, just keeps repeating. And that total error there is 0.0003. This is the actual observed error. So I want to compare that versus the error we get from the error bounds, which you might call the expected error. The expected error would be no higher than the error bounds. And the error bounds for Simpson's rule are a little bit different. So we've studied the error bounds for trapezoid rule and midpoint rule. This is going to look similar, but there are some differences that I want to go over. The first difference is rather than having a K2 constant, you have a K4 constant, which means we're going to look at the bound on the 4th derivative. So that is going to be a little bit different. Then you get b minus a to the 5th power instead of the 3rd, like it is for trapezoid and midpoint, all over 180 n to the 4th. So this is the error bound formula for Simpson's in this case. So it's going to look a little bit different. K4 is the bound on the 4th derivative. So I take the 4th derivative and I find on the interval, in this case the interval is from 1 to 4, So on the interval from 1 to 4, how bad does this thing get? Well, I've actually already gone in and looked at calculating the fourth derivative. And if you do that, the fourth derivative here is pretty easy to calculate. The fourth derivative of f, just using power rule over and over again, is negative 15/16 x to the negative 7/2. And let's see, if we bring in a graph of this, you can easily see that the graph of this, let me shrink that down a little bit. All right, that looks good. The graph of this is clearly going to have or obtain its largest value at x equal to 1. It is an increasing graph, so it's furthest away in this case at x equal to 1 because it's increasing, it's negative, so it's increasing up to 0. So it's furthest away at 1, and the actual value of the fourth derivative at 1 is, an absolute value, is 15/16. So 15/16 is our K4 value. All right, if we use the boxed formula over here for our error bounds, then the difference between I and S6 should be no bigger than K4, which is 15/16, times B minus A, which is 4 minus 1 to the 5th, over 180. N is the number of subintervals. So N was 6 for this problem. I'm doing 6 subintervals. So if you calculate that, you get 1/1024, which is approximately this decimal value. Now, because of that, the only thing I have to check is, did the error we observe, did it fall within this bound? And the answer is yes. So the actual error that was committed is less than the predicted maximum error that could be committed. So this error bound is actually working. We know that the error is no bigger than 9/10,000ths, and we actually showed that it's 1/10,000th in error, which is inside the observable range. So this is just a small glimpse at Simpson's rule and sort of how to construct the error intervals, how to look at the error bound. The error bound formula is a little bit different. It involves the fourth derivative of the function rather than the third derivative, so it's something that you need to pay close attention to. But for the most part, this works very similarly to trapezoid and midpoint rule. A lot of the calculations are the same, a lot of the ideas are the same. It's just sort of getting used to using these error bound formulas. All right, thank you for watching.